Hello everyone and welcome back to nuclear chemistry. Today we'll be talking about two types of nuclear reactions, which are nuclear fission and nuclear fusion. So you guys will be able to differentiate between these two types of reactions and just observe how the equations for both of these reactions look like. So basically, one thing that's common for these two types of reactions is that they produce a lot of energy. And that's one thing that makes them different from chemical reactions, is that they produce a lot more energy compared to the chemical reactions. But where does that energy come from? Well, that's one thing to keep in mind, that in case of both fission and fusion reactions, some of the mass of the reactants is converted into the energy. So that mass, the amount of mass that's being converted into energy is significantly low, which is why we do not count that in numbers. But still, that's something to remember, that energy is basically coming from the mass because some of the mass is converting into that energy, which is why we say that there's a slight difference between the mass of the reactants and the products in both fission and fusion reactions. Okay, so keep that in mind, that the reason why there's a slight difference between the mass of reactants and products for both of these reactions is because that mass is being converted into energy. But the amount of that mass that's being converted is significantly low, so we don't really count that in numbers. So nuclear fission is basically when we have a larger nucleus, or when we have one atom that absorbs a neutron and then it splits into two or more pieces. In other words, it splits into some other radioisotopes, it splits into some decay particles, and in that process, it produces a lot of energy. Now, two most common radioisotopes that do undergo nuclear fission are uranium-235 and plutonium-239. Okay, so here's how the equation for nuclear fission of uranium-235 looks like. What this equation is telling you is that a uranium-235 isotope is absorbing a neutron, and then it is splitting into two other isotopes, barium-141 and krypton-92. And it's also releasing three neutrons as well as some energy during this process. Okay, that's what this reaction is telling you. Now, nuclear fission is observed in nuclear reactors, atomic bombs, and all that stuff. And one way to remember that nuclear fission is splitting is the fact that fission has an I, just like an I in splitting. Okay, so and that could be a way to remember that fission is when we have one atom splitting into two. Okay, so nuclear fission can also start a chain reaction. And here's what that means. So let's say we start with an isotope of uranium-235, which absorbs a neutron, and then it splits into two isotopes. It splits into barium-141 and krypton-92. And in that process, it releases some energy and it also releases three neutrons. Now, those three neutrons will be absorbed by three other uranium-235 isotopes. Okay, and then all three of those uranium-235 isotopes will split into barium-141 and krypton-92. And then they will release three other neutrons again. And then those three neutrons will then go ahead and definitely, now we have 9 neutrons that are out there and they can be absorbed by 9 other neutron-235 isotopes. So that's how it starts a chain reaction, which can just go on and on and on and on and on. So nuclear fusion, on the other hand, is when we have two light nuclei. So nuclei is the plural for nucleus. So when we have two light nuclei and they are uniting to form a larger or heavier nucleus. So here's an equation for a nuclear fusion reaction. We have two different isotopes of hydrogen, which are uniting to form a helium atom, and it's releasing energy in the process. This is the type of reaction that produces energy in the sun. It produces energy in hydrogen bomb, and things like that. So one thing to keep in mind is that nuclear fusion reaction requires extremely high temperature and pressure. So sometimes what happens is that we need to get a nuclear fission reaction going so that it can produce a significant amount of energy to bring up the temperature and pressure to a certain level where the nuclear fusion reaction can also get started. But remember that nuclear fusion produces a lot more energy compared to the fission reaction. Okay, so the uniting of two things and releasing of energy is a lot more compared to one thing breaking into two. And then one way to remember that fusion means the uniting of two lighter nuclei is that fusion has a U, just like a U in unite. So if we have to compare the nuclear reactions with the chemical reactions, then the biggest benefit of nuclear reactions, as we mentioned earlier, is that nuclear reactions can produce a lot more energy compared to the chemical reactions. So when we talk about the risks and benefits of nuclear reactions, then basically pretty much the only difference that we have of these nuclear reactions is that they can produce a lot of energy, which we can use for a lot of things out there. We can use that to produce electricity, and a lot of things. Okay, but the risks that we have for because of these nuclear reactions are that uh, the waste that uh, is produced as a result of these chemical reactions can be significantly dangerous for life on Earth and for the environment. If there are some sort of spills between these between these nuclear reactions, then those could also be super, super, super dangerous for life on Earth and for the environment. So, and that's because these radioisotopes can decay and they can convert into other things, which is why uh, their hazards or their hazards can sometimes be unpredictable. So yes, nuclear chemistry can be dangerous, and it is dangerous. Okay, so that was this part of nuclear chemistry, and I will see you guys next time.